the next hour will be time well spent because I'll be covering a pretty interesting aspect of web application security. I'd like to talk about what browsers can do to, well, make web security better. The problem is that, okay. Oh, okay, yeah. Some AV problems. The problem is that web application security, I started doing that about, let me think, about 18 years ago, right? And back then I thought, okay, well, you know, security is always fun because you can break things and get paid for it, but eventually this field needs to die because technologies get better, developers get better, tools get better, but, well, it didn't work, right? So we're still here. Attackers are still running at full speed. There are high-profile attacks almost every week. And whatever you do, you know, teach people, invest in software, invest in hardware, invest in anything else. Whatever you do, it doesn't seem to help. So what I'm doing is that I thought, okay, let's look at it from the other end. So web browsers nowadays, at least most of them, they have pretty awesome safeguards against many attack vectors. And I mean, if you followed the browser war in the last couple of weeks, months, and years, you see that nowadays these browsers, they don't try to, you know, have programming features that only one browser supports. That was the browser war in the 1990s. But nowadays they try to be faster, more secure. And I mean, if you tried out the new Firefox version that came out 2 days ago, I mean, this is blatantly fast. This just shows where the progress is nowadays happening in the browser space. That being said, let's just have a look at many of those built-in browser features. Many of them can be activated by setting a certain HTTP header, and then we do have safeguards against some of the most prominent attacks. There's a pretty nice website actually. It's called securityheaders.io, and what you can do is you just type in a URL, and then you get a grade. So the conference website gets a D. Well, D is not that great, but I've seen worse. What essentially is happening here is that that website is just sending an HTTP request to that URL, and then checks which security HTTP headers are being set. So that's why the site is called security headers. So a D doesn't mean the website has any security issues. D just says, okay, this website doesn't use some of the security HTTP headers. And there might be good reasons for that, because some attack vectors just might not apply here, right? But still, so this should give you quite a nice impression, and if you do that for your own site and then scroll down a little bit, you'll also get a very brief explanation about what header does and how to apply it to your site. And I'll focus on some of the most interesting ones. I'd like to start with cross-site scripting. Now, this is a chart where the CVE entries are tallied, and this graph shows, starting with 1999, just how many cross-site scripting vulnerabilities were reported with the CVE number. And you see that, I mean, 2017 is still running for about 6 weeks, yet we have a new all-time high. Right? So this problem is not gonna die. And I mean, I've said that before, cross-site scripting will die, cross-site scripting will die, because the attack is trivial, and the countermeasures are trivial as well. But still, it doesn't seem to work. But, I mean, it's 2017 now, and I'm standing here, and if we meet next time, maybe next year's conference, come up to me and remind me that I've said that, but I'm stating now here today that cross-site scripting is gonna die. And I'll show you in a few minutes why I think that cross-site scripting is gonna die if you will cooperate, okay? But first of all, and I mean that cooperation usually comes really cheap, but sometimes there's some extra effort required. But we'll talk about it in a couple of minutes. Before I do that, we have to talk about cross-site scripting. Now, I am aware that all of you are very well versed in cross-site scripting. Therefore, this might not be news for you, but it is important when we also discuss countermeasures that apply here. The reason cross-site scripting is A, dangerous, and B, not as dangerous as it could be, is the only security mechanism for JavaScript that we have. And I mean, you all know the story, right? JavaScript was spec'd and implemented in mere 10 days, right? And in those 10 days, probably on the last day, like 3 hours prior to the deadline, they also thought about a security mechanism. And what they came up with was the so-called same origin policy, using the origin term from the IETF. Now, I don't like that origin term, because origin kind of sounds like where does code come from? But that's far from the truth. What origin in a JavaScript context means is rather the security context under which the JavaScript code is running. So if you are on, let's say, world.phpart.com and you load a JavaScript library from, let's say, Google CDN, what is the origin of the JavaScript library? Well, it's not the Google CDN, it's world.phpart.com. Because the JavaScript code runs in security context of the HTML page that includes or loads or contains the JavaScript code. That's why I don't like the origin term. Security context is much better. But well, it's called the same origin policy. Now, the origin consists of protocol, domain, and port, and this all has to be the same. So, for instance, I have a couple of URLs here. Those 3 URLs here on the top, they have the same origin, right? Because they have the same protocol, HTTP, they have the same fully qualified domain name, example.com, and they all use port 80, either implicitly or explicitly. However, the 8 URLs down there are not 2 of them who have the same origin, because there's always something different. The protocol, the domain name, the port, or even several of those. And that's the problem. And that shows the problem of cross-site scripting. Because cross-site scripting, most of the time, works like this. An attacker manages to inject JavaScript content on your page. The same origin policy protects us from some attack vectors. But on the other hand, if we manage to attack a JavaScript code on our page, that code runs with the same security rights, with the same privileges as our own JavaScript code. And that's what makes cross-site scripting so pretty damn dangerous. And therefore, we need to defend against cross-site scripting. Okay, quick question. When you have a look at the history of browsers, there was one browser and one browser version that really made security a top priority and said, okay, we have now new security features. Our browser will be the most secure browser ever. Which browser is that? No, Chrome is about getting data. And being fast, I have to say that. Second, Opera. I think when Opera was started, Opera was about getting $29 in order to remove the S. But I'm not sure about that. No, that browser is, I'm shocked that you don't know that. I can't even believe it myself that is true. That browser is Internet Explorer 8. No, really. Internet Explorer 8 introduced several security HTTP headers. Plus, of course, a lot of security vulnerabilities and bad performance and everything, but still, those headers were in there. And one of the headers invented by IE8 and then adapted by Chrome and Safari and Edge and, well, all the other browsers. Except for, there's one name missing here. Let's talk about that a little bit later. But most of the other major browsers, they also implemented the same thing. It's a cross-site scripting filter. And the idea is pretty simple. So there's a filter included that tries to find out whether there's a cross-site scripting attack. And when Microsoft created that filter, they had 2 design goals. The first design goal was that filter has to be fast, right? Of course, if you load a page and there's some machine learning going on and whatever, data crunching, and after 30 seconds the browser tells you, okay, there's no cross-site scripting here, you can now work with the page, that doesn't cut it, right? So it has to be super fast. And the second design goal was, this cross-site scripting filter must not create false positives. So the filter needs to be absolutely sure that there's a cross-site scripting vulnerability. It must not happen that someone is doing some fancy stuff in their code, and then the filter says no, that's an attack if it isn't. Right? So that filter is not perfect. And if you have a look at those browsers and the filters involved, And the results, there are some attack vectors that some of these filters catch and some of them don't. But basically, it's a good thing. And if you use one of those browsers and go to the settings and then try to say, okay, let's deactivate that filter because my code doesn't run any longer with that filter in place. No, that doesn't work. As the end user, you cannot deactivate that filter because cross-site scripting, I mean, in the end, it hurts the user. But cross-site scripting, since the code runs in the security context of the website, it hurts the website. So the only entity who is allowed to turn off that filter is the website. We have the HTTP header XSS protection. And if you set it to 0, then that filter is deactivated. The user can't do it. If the filter is activated and the filter catches something, you get either a message in the console, or if you're using IE 8, 9, 10, or 11, then you get this nice banner here that the page has been modified to help prevent cross-site scripting. So yes, there were like a dozen of lawyers kind of coining this, because they could have also said, okay, we prevented cross-site scripting, but you don't know whether you did this, so we helped prevent cross-site scripting. Oh well. So it's a good thing, right? So we have this kind of nice filter here in place, but on the other hand, it only finds a few attack vectors, but not all of them. Especially if we have stored cross-site scripting. So the attacker sends JavaScript. JavaScript is stored in a database. Then all users who open up a page get their JavaScript code. That's impossible to block by this built-in cross-site scripting filter. Therefore, we need something else. Now, I promised you a few minutes ago that cross-site scripting is going to die, and now I'm going to show you how that will be done. And I'll be doing this by something that no non-Microsoft invented. It's called Content Security Policy, and it's a W3C initiative, a standard. And what it basically does is that a web server creates a policy telling the browser which resources to load, run, execute, process. So basically you tell your browser, okay, this is my website. All my images come from that server. All my JavaScript comes from here. All my style sheets are from there. And if there's something else going on that page, which might be a trace of cross-site scripting, then just don't do it. And this is pretty amazing, and I'll show you how great it is if your website is compatible with it, but we'll talk about it in a bit. There are 3 versions of Content Security Policy. Version 1 was for long candidate recommendation, so it's the step before being an actual standard. And was that for years, but you know, standardization takes a lot of time with the W3C. So what basically was happening is that all of the other parties involved and the browser developers, etc., they already started working on a second version. So eventually W3C pulled the plug and just said, okay, version 1 is just a working node. Let's just go with version 2, and version 2 is a recommendation for 11 months now. There's already work going on for version 3. The latest working draft by the W3C hasn't been updated in over a year, but the editor's draft, where you add commas and then remove them later, that has been updated a month ago. So there's still work going on, but version 2 is the interesting version. Actually, before we talk about so the question is, why is 2 more interesting than 3? Because there's browser support for 2 and there's 0 browser support for 3. So that makes 2, at least for me, more interesting. From a feature perspective, I'm with you. Then 3 is more interesting because they're adding new stuff. Okay. But browser support is a great point to make. So let's have a quick look how well the browser support is, and there are good news and bad news. So Content Security Policy version 1.0, I see all green here. Isn't that fantastic? I mean, we ignore Opera Mini, of course, but all green. And I mean, even IE is kind of green. And if you work with Can I Use, then you know that this lime green, or whatever that color is called, usually means almost complete support, right? Not complete, but almost complete. There is one exception in the whole long list of Can I Use, and that exception is this, because here, that lime green means one feature, exactly one feature, is supported. And it's a feature that is not useful. Okay, so in my book, IE doesn't support Content Security Policy version 1. Bummer. Is that a bad thing for us if we want to implement content security policy? No, it is not, because, well, if IE users, they were unprotected until now, and they're still unprotected if we have a security issue in our code. But all the other browsers, they are safe. What about version 2? And in version 2, we see, oh no, look, Firefox. Firefox is lime green here. What does that mean? Yeah, there are like 1 or 2 features that are not fully supported by Firefox. So basically, Firefox is green, right? So that's a different lime green than that lime green up there. The only thing of note is here the Edge browser. So the Edge browser has full content security policy 1 support since its beginning, since the very first version of Windows 10. Content security policy level 2 is only supported since Edge version 15. Edge version 15 was the one that came with the, I think it was called Creators Update in April. So there was another one last month, but the one from April this year. So if you have that version, then you're compatible with content security policy level 2. There are ways to have kind of a backwards compatibility when you try to create a policy that both works with version 2 supporting browsers and version 1 supporting browsers. Yeah, so the only browsers that you can help by using that backwards compatibility technique are essentially Edge 14, 13, and 12, which have a market share of I think 10% or something. So probably that's not that crucial. All right. So how does that generally work? Let's quickly have a look at some of the features, because I'm really excited about that technology. So the server sends an HTTP header. And that HTTP header is called content security policy. If you see in some, documentation or blog post one of these other header names, then resource is outdated. So content security policy is the header. There's also an alternative for all browsers that supports content security policy version 2. It's by using a meta tag. So you don't even need something on the server specifically. You can just put it in the HTML. There are some content security policy features that do not work when you use a meta tag. But for most applications, this actually is good enough. I will still use a header today. All right, and how does that look like? So we have the header, and then we have so-called directives. Directives are the things with the dashes. So we have default SRC as one directive, and we have image SRC as one directive. As you can imagine, I mean, the names are kind of self-explanatory. So image SRC basically means if I have an image tag on my page, if I load images, where may I load them from? After a directive, you have a set of values separated by spaces. So here just have one value. Okay, all the images come from this server. Default SRC is the mother of all directives. So if a directive is not set explicitly, its value is taken implicitly from the default SRC directive. What I'm saying here is default SRC set to self in single quotes. Single quotes in content security policy means there are constants, special values, and self means origin of the current page. So this basically means, okay, everything I'm loading, images, not images, sorry, we have a different directive for that. But images, not images, style sheets, web fonts, JavaScript, plugin data even, they can only be loaded from the current origin. All for images, they must be loaded from static.example.com. There are many more features. Just let me show you a few of them, and I put a lot of info on that slide so that if you have a look at the slides afterwards, you just have a full reference. So basically, we have default SRC and then many others. Media SRC, for instance, for video and audio data, or font SRC for web fonts, or connect SRC for anything I connect to via Ajax or WebSockets, for instance. So a lot of things you can set. Now, when we talk about the values for those directives, you have already seen a few. We can provide an origin, and we have self as a constant, and there are other constants as well. And this is I don't actually dare to switch to the next slide, because usually a standard is supposed to be unopinionated, right? Content security policy is. Actually, let me show you an example. I set up a let's say an enterprise application. So what this application does is, it shows a logo, and then it shows the current time. And the way it's doing that is that it is contacting the server once a second and gets the current server time, right? So because we are professionals and you can't have enough layers in your application. This is how the code looks like. I hope you can see it all right, right? So it's plain HTML. Here I set up the calling the server once a second. And since I would like to wanted to add some spice, I'm not just outputting text like an amateur. I'm using libraries, so I'm using the underscore library because I need a template library. So you can't have enough template libraries actually in your application. And well, you're laughing, but you'll actually be crying when you see the effects of that. So here's my code. So I do the XML HTTP request, or I set it up. And then I call the underscores template method and create a template which I would like to output. Current time, colon, and then the current time, right? And whenever I get a time from the server, I call update time, and update time sets the output element to, and then I parse the template. So that looks kind of nice, right? Doesn't it? I mean, it's a nice application. Now let's add content security policy. And I'm doing this by setting a header. I'm using double quotes. So content security, it's hard to see. Content security policy. Okay, typing is a challenge today. Sorry for that. So default src self. Okay, I mean that sounds reasonable, right? I just say, okay, load everything from the current server, because that's probably usually what you start with, right? You have just one server, all your resources are on there, should work beautifully. And if I reload this page, it looks a little bit different, right? What's the first difference? The most striking one probably, the logo ain't there anymore. Okay, why is the logo not there any longer? Let's have a look at the HTML markup. I've been stealing the logo from the conference's web server. Okay, so of course content security policy prevents me from doing that, unless of course I change my policy. So I'm adding image src, and then I just copy and paste the origin of the URL. And I mean, maybe later I'll add some images on my own, so I just say, okay, all the images can come either from the conference web server or from my own domain. So it looks much, much better now. But there are more problems here. The current time text, A, it's extremely small. I could read it much better in the old version. And B, where is the time? Now, there are two problems involved here, but they're actually the same problem. Why is the text so small? Yes, please, question. Yeah, that's perfectly fine. It worked before. Yeah. So the question was about that interval call. There is some reason why I did it that way, and I'll explain it in just a bit. But basically, yeah, when you use set interval in JavaScript, you can either provide an anonymous function or a reference to a function, or code as a string. So that because in 1995, I think there were anonymous functions, but no one was using them. So that was actually the approach. It did work, right? But yes, it has something to do with the content security policy that it stops working. But let's maybe first go for why is current time so small, because there is no explanation why current time is so small, right? But there's no code involved. The only thing is here that I set the font size to XX large. Now, how does cross-site scripting usually work? Cross-site scripting usually works by someone injecting, let's say, script alert 1. So inline code. And one of the effects of content security policy is if you have a content security policy that applies to or that covers JavaScript, and this one does because, as I mentioned, default src gives us default values for all the other directives. So if you have that, inline code doesn't work any longer. That same thing applies for inline styles. that's an inline style. And since I have a content security policy covering styles, because I said default SRC, that inline style is ignored by the browser. That inline code here is ignored by the browser, right? Because the browser says, well, that is inline, I will not execute it. And before we proceed, let's think about cross-site scripting for a second. So cross-site scripting works by an attacker injecting script alert 1. That's inline code, which doesn't work. So that attack vector is closed. What else could happen? An attacker injects script src equals http attackersite.com/bad script. Doesn't work because I've set default src, I could also set script src to self. That attack vector is closed. So what is the only way that cross-site scripting could still work against that page if I can only run JavaScript code from my own server? Yeah, if an attacker manages to upload JavaScript code to my server, and in that case, cross-site scripting is the least of our problems. So that's actually pretty nice. Now, we somehow maybe want to, still enable inline JavaScript code because it's so cumbersome to convert this into external code. Well, it's not cumbersome, of course. I could just move that code over to the JavaScript file. But still, there might be areas, or there might be cases when you want to externalize, where you cannot externalize your JavaScript code, so where the JavaScript code needs to be inline. It's not a good idea, and therefore, the authors of the content security policy specification, they said, okay, let's make an opinionated standard. When we have such a directive, and we like to set a value to that directive, we can use, as I mentioned, the origin, we can use self, we can use a few other things, and there's two special constants. So, we can set it to star, which no one should do, origin, we can set it to URI, we can set it to self, to none, and then to unsafe inline and unsafe eval. Unsafe inline. So, I mean, you could call this constant activate inline or enable inline, but unsafe inline, that's opinionated. But it's a good thing, because just imagine the pain. I mean, imagine the pain I'm feeling now, right? So I'm talking to you about security, and I go here, and then I just, and I mean, really, it hurts my fingers. Unsafe. I cannot type unsafe, right? Unsafe dash inline. Oh, that hurts. That hurts a lot, right? But well, so that's the reason for that. It's really very opinionated, but it's a good thing, because if you want to allow inline code, it's unsafe. But maybe the applications are running, and well, at least the font is larger. Yes. I was about to explain. Just let me finish the sentence. The enlightenment will come. Just so there was a question about what did the unsafe inline change, and what I was about to say was that now at least the current time has now the big font size again. Why? Because the inline style sheet is now being activated again, right? Content security policy prevents inline, unsafe inline enables it again. However, there is still no time being displayed. And, well, we could try to look at the F12 tools in the browser and see what they are complaining about. And, well, actually, if we increase here the font size, uncaught eval error, refused to evaluate a string as JavaScript because unsafe eval is not set. Ah, okay, so among other things, content security policy does not only deactivate inline code, it also activates calls to eval or dynamic code execution. So in JavaScript it means eval, it means the function constructor, new function. It also means providing a string to a function like setTimeout. That's what bites us here, but there is more. And that's, in my opinion, one of the main problems when using content security policy, especially for a legacy application. So we are using underscore here as our library of choice. And let me see where there it is. And I mean, I'm not dissing the underscore library here at all, right? It's a great templating engine. However, there's one thing that we need to keep in mind. There is a template method which we are calling, right? Here it is. Now, let's have a look at that template method. And what the template method does, among other things, is, sorry, here, you see that there is a source variable, and that source variable is like a concatenation of strings that look like they contain JavaScript code. Let's scroll down a little bit. More JavaScript code, more JavaScript code, and yeah, more JavaScript code, and then that code is returned, and then when we have that code, let's have a look at our opposite code, then we execute the code, right? So the underscore library is using eval, technically, which means if we use that library, we have to activate eval. If it's our own code, we might work around this, but in that case, we can't. So yes, we would need to go one step further and also allow, and it hurts again, unsafe eval. And now that we are doing this, the application runs again. So I've shown you the good and the bad things here. Content security policy is super effective, and browser support is great if you ignore IE. But for IE users, the situation doesn't change to before using content security policy. But on the other hand, especially if you have a legacy application or if you have a framework that uses a lot of inline or a lot of libraries that use eval, then this might be cumbersome. I mean, the best strategy is working like you would do when you set up a new application. You externalize all JavaScript, you externalize all the style sheets, all from a performance point of view, great ideas. And then you can try to apply a content security policy. And that works really well. For legacy applications, it really depends on how that application was made. I recently visited a customer, and they have used Apache Wicked as their framework of choice, Java-based. And that framework is spitting out inline JavaScript code like I've never seen before. So I think about 90% of the output of the HTML page is inline JavaScript code. We talked about content security policy. And all we did find was an entry in their ticketing system where people said, could we kind of make this more friendly for content security policy? And, well, they essentially said, oh, no. Why content security policy? Security is not interesting. Well, so that's the things that happen, right? So it's a great technology, and I really encourage you, no, I urge you to consider applying this to your application. Many websites are doing this. But yeah, it's not perfect because it requires some effort from. All right. Yes, of course. That's a very good point. So in my example here, I went the quick route, right? So I didn't completely refactor the application. I just said, okay, it doesn't work. I enable all of the bad features like inline eval. So now, if I had a cross-site scripting vulnerability in my application, I would have now one back, right? Yeah, so the better way, of course, would have been to externalize all the JavaScript code, externalize all the style sheets, and then drop the templating engine and just, create my HTML myself. Yeah, so absolutely correct. No. So the additional question was about what about other frameworks like more common ones. Angular and Vue were the ones you mentioned. So they usually they avoid inline code, right? Because you always reference external files and then just parse the DOM. So they are exempt from that, so to speak. So you do not need unsafe inline in order for them to work. And at least in the current versions or the last ones I checked, you also do not need unsafe eval because they do their templating engines differently. They do use eval calls. I mean, because they have very modern frameworks and they know that eval not only is a security nightmare, it's also a performance nightmare, right? And therefore, so they work exactly as expected. Okay. Thank you. Great question. Yes. Sorry, a second. What's inline? Nonce. Okay. Yeah. Yeah. So the question was about nonces. That's one of the other features of content security policy. So the idea here is, and we don't have time to cover this in details. No worries. But I'm happy to explain it. So the idea is, okay, you do have inline code, and you want that specific inline code to run. So there are two ways that content security policy version 2 supports. One is if you have an inline script block, you give the script block an extra attribute, nonce equals, and then a random value, and the same random value is in the content security policy. So you as the website creator, you set that random value and then also set the attribute. An attacker that abuses a cross-site scripting vulnerability cannot guess that random value. So that would work, so a nonce would work. Another option is if you have specific inline code, you can also calculate the hash, the SHA 256, 384, or 512 hash, and then put that hash also in the content security policy. So that specific code is run, but no other code is run. So these would work. So there are several workarounds for that, including that one. So thank you very much. That's only in CSP2, yes. So if you use that, you have a hypothetical problem with old Edge versions. But the thing is, if you combine this with unsafe inline, then CSP1 browsers see the unsafe inline, CSP2 browsers see the hash or nonce and ignore the unsafe inline. So that's one of these great backwards compatibility hacks, which I find actually very, very useful. But yeah, again, so the only browsers that are essentially affected by that are older Edge versions, because in IE the support is so limited that it just doesn't make sense. All right. So let's move on to let's go to another threat. Let's go to cookie hijacking. The problem is that HTTP is a stateless protocol. We cannot remember anything, so we had to create hacks, and those hacks were created in 1995 already by Netscape, and one of those hacks was cookies. So a server sends data. Client stores those information and sends it then back to the server, right? It's a great idea, but the problem, of course, is that these cookies, when they are in the client, they can be manipulated. On the other hand, most authentication schemes more or less trust those cookies, so we need to protect those cookies. The cookie usually is the only piece of information that identifies the user with the web application. So if the cookie gets stolen, someone can impersonate us. And the major threat here is called cookie hijacking. Now, and I find this really, really amazing. Even in the 1995 Netscape cookie specification, they already saw some need to protect those cookies. So one of the values there they provided was the secure cookie option, which says this cookie can only be transferred via HTTPS. I mean, we are all here in the same Wi-Fi network, I guess, right? The conference venue's Wi-Fi network. So we can all eavesdrop on the other communications here in this room, or even in the venue. If it's not HTTPS. If it is HTTPS, we have end-to-end encryption, so we cannot eavesdrop. So therefore, this is a great thing. So always use HTTPS whenever you are using cookies. And even if you don't use cookies, always use HTTP. But there's another thing, and that was invented by, yes, IE8. Incredible. A new cookie option called HTTP only. This kind of hides cookies from JavaScript. So if we use JavaScript to access document.cookie, those cookies with the HTTP only option set, they are not shown, which is a good thing. Well, there are some kind of workarounds for attackers, but the web server has to be set up in a really crazy way in order to get access to those cookies. So basically do that. There was a long debate in the PHP community whether to automatically activate HTTP only for session cookies. Because some people say, no, I have some funny application that uses JavaScript to access the session cookie because well, there was no good reason coming after because, but well, that was actually the reasoning while this mandatory step was delayed for, I think, 2 years or so. But since a while now, all the session cookies that PHP is using, they have HTTP only set as well. Do not change that setting. Since I already mentioned HTTPS and how important HTTPS is, there's another standard I would like to briefly cover. and that one is called HSTS, or HTTP Strict Transport Security. And that's another pretty great idea. The aim is to enforce HTTPS, which is a good thing, right? Because no one's cookie is being stolen. But let's just imagine you have your website, website.com, and you want to enforce HTTPS. So the user types in website.com in their browser, hit enter, and then, well, the browser sends an HTTP request to, since there's no protocol provided, http://website.com. Now you do your thing, right? So on the server, you do a redirect to HTTPS, or you rewrite the URL, however you're doing that. But the first request is unencrypted. And if there may be some cookie information coming along with that request, those cookies might be stolen, right? So that's the problem at hand here. Now what strict transport security does is pretty amazing. If the server sends the strict transport security HTTP header to the browser reads that header, and the header instructs the browser to never do an HTTP request to that site again. Only HTTPS for a certain amount of time, max H. And this can also apply to subdomains as well. Pretty amazing. So once this header is set, even if the user explicitly says http://website.com, the browser does a request via HTTPS. Really, really amazing. But it's even better. All modern browsers, they have a preload list. This originated at Google for Chrome. So if you go to the Chromium source code, you actually see that preload list. And you can also apply that your website is added to that preload list as well. If your website is on that preload list, the browser, even for the very first time, doesn't do an HTTP request. It does an HTTPS request. So if you are absolutely certain that from now on, you will only allow HTTPS for your web application, no matter what, apply for the list. And applying for the list basically means that you send a specific version of that HTTP header, and then fill out a form, and then they automatically test it, and basically that's it, right? Then you're part of it. But make sure that you always want HTTPS. If for some reason you say, well, but I do have this HTTP endpoint, then don't be put on that list, because then that HTTP endpoint will not work, because it will not be reached. But pretty amazing technology, and therefore I'm pretty happy about that feature as well. You could also use content security policy to enforce HTTPS. There is a directive for content security policy called Update Insecure Requests, which basically does the same thing. So if on your website you load a resource or you have a link, and the link uses HTTP, then Update Insecure Requests automatically turns this into HTTPS when the user clicks on that. So that's pretty nice. The browser will then also send an HTTP header Upgrade Insecure Request :1 in order to provide us with support here. That's a nice feature, and I would take this as an additional measure. However, I'm more convinced by HSTS because it's the more generic solution, and also the preload list feature I think is pretty amazing here. What you can also do, of course, is that you use default SRC HTTPS as a kind of a directive in CSP, so that every resource that is being loaded must be loaded via HTTPS. If it's not loaded via HTTPS, you block it from being loaded. So there are different approaches to achieve more or less the same goal, but if I could only pick one of those measures, I would definitely pick HS. All right. One additional aspect, and I just would like to cover it briefly, is HTTP public key pinning. Right, so that's the basic idea here is that if you have, let's say, certificates or signing requests or other cryptographic entities, HTTP public key pinning kind of provides a list of those entities which can be trusted. So whatever, if you have a HTTPS certificate, then you can use the HTTP header, public key pins, and then you provide just the hash of your certificate. And if the certificate doesn't match because someone, I don't know, does funky stuff in your wireless, or there's some additional certificate that was not issued without you knowing it, and that threat can be found and mitigated as well. That's of all of these HTTP headers. This is probably the most specific one, and also the most niche one. And that's why I said at the beginning that at Security Headers IO, if you don't get an A, that's not always a problem. It just depends on which of those HTTP headers you have been using and which of those you have not been using. All right. One more major threat, and well, there is no direct protection for that threat, but for an additional advanced version of that threat. It's cross-site request forgery. So these are the CVE numbers for cross-site request forgery. So you saw the first time this was actually being actively used and called cross-site request forgery was 2002, so 3 years after cross-site scripting. And in the new OWASP top 10 list of 2017, cross-site request forgery fell out of that list because the OWASP says it's now number 13 according to our numbers. According to my numbers, it may have been the case in 2016, but 2017 looks entirely different. And I'm a bit afraid that people started to learn about web application security will never hear of cross-site request forgery because it didn't make the list. So that's actually pretty sad. But I mean, there's nothing you can do with HTTP headers against cross-site request forgery. But there is another thing. It's called clickjacking, and I'd like to show you how that works really quick. So let's go to our application here, and I have a page. It's called delete my accounts.php. That's very bad because there's a button on that, and if I click on that button, it says no party tonight. Okay, this is something we need to avoid at all costs, right? You know, 6:45 at one of the sponsors. You heard that in the morning keynote. Now, what does this have to do with what I want to show you? I have a page here that is called clickjacking PHP, and what I basically have here is a link to Google, some suspiciously blank lines, and some CSS. So let's go back here and then go to clickjacking.php, where we just see the link, right? So the link goes to Google, and those in the front rows maybe can actually see, yeah, it really goes to google.com. There's no JavaScript on that page, but the problem is when I click here, it still says no party tonight. So what's the problem? The problem is that here in these blank lines, if I scroll to the right a lot, we see that I've loaded the delete my account page in an iframe, and then use some CSS to put the link above the iframe. We can see that actually when we change the CSS a bit. So if I reload this page now, you see that, yeah, the button happens to be exactly underneath the link, right? So I click on the link, but I actually click on the button. And that attack is called clickjacking. It's like cross-site request forgery, but the user is actually doing the click. Which is really bad, because you cannot say, I've been attacked, because you have clicked the button. So what can we do against this kind of attack? Well, why does this attack work? The attack works because my page with the button can be loaded in an iframe. So if you go in your coding archive, right, so you look at the code you have written in the 1990s, and you have some frame-busting JavaScript code from back then. Use that code from back then, really. It may say script language equals JavaScript, but it still will work. However, there are better options now. There's one option that was invented, of course, by the best secure browser on Earth for a week. Internet Explorer 8, the X-Frame Options HTTP header. The X-Frames Options header, if set by the server, says, okay, this page can not be loaded at all in an iframe, value deny, or can only be loaded in an iframe on a page of the same origin. So there's the origin again when you say same origin. Pretty effective. And I mean, if you have a web application and someone is auditing the web application, even if the auditors are very incompetent, one thing they can do is they check your HTTP headers. So they just look for the X-Frame Options HTTP header, and if you don't have that header, they will say you have a security vulnerability. I mean, you saw, it's kind of tricky to kind of demonstrate clickjacking because I had to know exactly where I wanted to click. But finding out whether there's insufficient protection, that's really easy. So just set that header so quickly. You set the header, and that complicated attack is just not possible any longer. If you use Content Security Policy version 2, you could also use a directive called frame ancestors, which basically says if this page is framed, on which pages is that allowed, so you can have much more fine-grained control. The problem with that approach is, of course, browsers that do not support Content Security Policy version 2 because they're 100% unsupported and unprotected. Therefore, the XRAM options is, for the time being, at least until IE dies, the best option we have here. All right, that's basically, these are basically the most important attacks. There are two more aspects which I'd like to tell you about in the few remaining minutes. One is called MIME type sniffing. We have the content type HTTP header, which tells the browser what kind of file is coming in, right? So you see that when you, download a PDF, and then it's displayed as a PDF by the built-in PDF reader. However, some browsers, they are named here, they try to guess the MIME type, right? So they don't look at the content type, they try to guess the MIME type. And we don't want this, actually. Because if you avoid guessing the MIME type, that reduces the exposure for drive-by downloads, right? So you know that, for instance, Chrome, good example here, Chrome doesn't ask you, download this file, yes, no. It just starts downloading, right? And then the file, resides somewhere on your system, maybe gets executed. And so the exposure to drive-by downloads can be just reduced by that technology. And also the risks of user-uploaded content that with clever naming could be treated as a different content type, like an executable file. Right? So this is the idea. Also, just one HTTP header being set, auditors will look for that specific header, just set it to no sniff, and many of these attacks are hypothetical, but still, just do it, and you're safe from both attackers and auditors. And there's one more thing I'd like to show you, and that's rather new because it's still being worked on. But I think this just shows that all kind of attack vectors are considered and try to be protected by browsers, because we as developers just mess up too often. And the threat is data leakage via referrer. So just imagine in the good old days, you had a web application, or not the good old days, actually in the sad new days, you have a web application and the URL is telling you something, maybe a customer ID. Let's just imagine that you log into something and then you're in website.com/customer/ and then your customer name, because we all love REST, right? The problem is if on that page is a link to an external site or an image being loaded from an external site, the HTTP request there sends the current URL in the referrer HTTP header. So the target site now knows the page from where we were coming from on the page you have just loaded in your web browser. This might lead to data leakage, because target site has no business in knowing exactly what URL you are on currently. And therefore, one approach that W3C is still working on, but it's not finished yet, it's an editor's draft, is the referrer policy, which allows us to kind of restrict, okay, who sees the referrer? So, for instance, origin. The referrer can be seen by all sites of the same origin, or no referrer, so no one is seeing the referrer, and many other options. Right? So pretty interesting, and basically this just shows that the browser is becoming actually our main safeguard against attacks. All of these HTTP headers are no excuse for us to just ignore security, right? Because you could also say, hey, I have content security policy, I can have as many cross-scripting vulnerabilities in my code as I want. But no, defense in depth is the key. So try to close all security vulnerabilities and avoid them at all costs. But also use those HTTP headers we discussed today in order to use the browser as your second safeguard against any kind of attacks. And this list of HTTP headers will become larger and larger in the next few years. And I'm pretty excited that browsers now are not just tools to display content, but also to make sure that content runs without any security issues. And with that, I say thank you very much. Have a great last day at the conference. If you do have the time, please rate this session on Join-In, where I'll also upload the slides later today. And with that being said, thank you very much.